I'm Antonio Sala, and in this video we are going to finish our example case study of multi-output Gaussian stochastic processes, and we'll deal with prediction, and in particular with prediction of the latent factors we used to build our covariance in our statistical model. Let us briefly review what we are talking about. Before such review, I just hint that what we are going to do, predicting some hidden variables that multiplied by a matrix give me a set of observable outputs, well, that's sort of similar, well, it's actually the same, let's say, with certain assumptions, that what in control is called the Kalman filter or the Rauchtung-Schriebel smoother. We'll say it again later when we have written all the formulation, but we are actually doing something similar to Kalman filtering and smoothing, but instead of having differential equations, in here we will have covariance kernels. Okay, as I said, let us first summarize what we are talking about. In previous videos, we discussed how to generate sample realizations of a two-output Gaussian process in which I have a common component, the dashed yellow line here, with a given power spectral density, with a given covariance kernel, and then some specific components that wiggled up and down from that common component. So we got realizations, something like this, or this, in which, well, the common component had, let's say, opposite influence in each of the two observable outputs. As I said, my statistical model was built on the assumption that I had some internal factors, internal latent components that could not be directly observed, and I only observed those components multiplied by a matrix C, maybe with some measurement noise, and then the covariance of the observable outputs, which I used for output prediction, output smoothing, let's say, will be, well, the covariance y transposed, y is Cu, y transposed is U transposed, C transposed. Of course, when we are dealing with stochastic processes, we need a covariance between outputs at different input abscissa points, x1, x2, let's say. So we are referring to the covariance of Cu of x1, U transposed of x2, C transposed. U is 3 times 1 vector of latent internal factors, and y was a 2 times 1 vector of observable outputs. If we think in zero mean, so that we don't need to bother with the incremental units about the mean, whatever in formula, then if we extract the constants C and C transposed from the expectation of U transposed will be a big K matrix with a covariance kernel in the diagonal of each of the components, and this will be C big K diagonal times C transposed. And that was my statistical model, and in my example in particular, this big K was built with these 3 independent in the diagonal squared exponential covariance kernels, but okay, you may use any kernel you wish from literature. And the C matrix was this one, saying that the first component appeared with opposite sign influence in each of the two outputs, and the second component only appeared on the first output, third component only appeared in the second output. So this was my statistical model and allowed me to build this kind of 2 times 2 covariance matrix like that. Well, the thing is that in the actual code we used an equivalent representation in which, instead of considering my Gaussian process as a 2-output thing whose covariance kernel was a matrix, I could equivalently consider it to be as a 1-output thing with an augmented input in which, apart from the abscissa numeric, I got a categorical variable, an index telling me if I referred to output 1 or 2. So I could write a covariance matrix function of the two augmented inputs, xi1, xi2, that of course I should suitably encode that this thing should return the appropriate element of this 2x2 covariance matrix. With this code and these covariances, we were able to generate sample realizations of these two output stochastic processes. And if we had some samples, in blue samples of first output, in red samples of second output, we were able to compute the suitable covariance matrices between these sample points and test points. We were able to carry out prediction of the outputs at intermediate points in both mean and variance confidence interval. So we got this kind of predictions in which we emphasized in previous videos that a joint prediction taking into account the correlation between these two functions enabled us to make predictions with a smaller error uncertainty, posterior variance, than if I used only marginal predictions as in standard Gaussian process regression. But from an abstract point of view, we were doing standard Gaussian process regression in this augmented input representation. So nothing new from a mathematical point of view, but from an application, engineering, and nice plot point of view, then okay, this may be an interesting example. So our problem statement now is that, well, imagine that the components in particular did not come from God, but they have some interesting physical or technological meaning in my application, so I wish to estimate them. Can we estimate, for instance, this yellow thing from samples of the blue and red functions? Well, I mean, it seems that this shouldn't be so difficult because most of what I see in blue and red functions comes from the yellow one. So, this should be easy, and indeed it is. Let's delve into the details as the main goal of this video. We have these samples, and from this Y we wish to predict U. Then, well, if we change U by X, we control people, we use X, but okay, in here we cannot use X because abscissa was named X. In control, abscissa is named time, and the internal variables not directly observable are called states X, but apart from the change of notation, this is the same as we are doing in control. We have some internal variables that behave according to some differential equation, well, to some stochastic differential equation with some random inputs and whatever. Those internal variables cannot be directly measured, so we measure some outputs and we want to estimate the internal variables. Then in control we call that state observation, Kalman filter, or RTS smoothing. And in here in statistics, well, you call it latent factor estimation, latent variable estimation, internal component estimation, or whatever. Just two ways of doing the same thing. With suitable math about stochastic differential equations and covariance kernels from stochastic differential equations, we would get the same result from a suitable Rauch-Thun-Schriebel smoother than the result we are going to get here. But okay, if that Rauch-Thun-Schriebel Kalman smoothing is unfamiliar to you, don't worry, this is just a comment to control engineering audience, because I guess that as I am a control engineering, maybe most of my followers also swim in that river. But okay, let's go with the detail. If we recall the basic optimal linear prediction, conditional, Gaussian, whatever, in order to predict A from B, where B is the information and A is the variable to be predicted, I need to compute the covariance between A and B, covariance between what I wish to predict and the information, and also I need to compute the variance of the information, sigma BP, and well, with some mean and posterior variance and whatever, I can use standard conditional normal formulae to predict this. I mean, we'll see them in code in a minute. So, if we wish to predict our components from our samples of the function, then it means that A are the components U and B are the samples at a given abscissa X and with a given label I, 1 or 2, depending on what I have measured at location X. So the covariance of this information stuff was already discussed in previous videos to make predictions on the outputs. In the previous videos, instead of U, this was Y, the thing I needed to compute here, the covariance. But in here, well, I need to compute covariance between a given component, Uj, let's say, U1, 2, or 3, at some points, x1, which will be a bunch of testing points in which I wish to plot. I need to predict the covariance of one of those 3 components and one of those 2 possible outputs, f1, f2, or well, I also call them y in some other slides, but okay, y is f of x, let's say, 2 of them. And these x2 points will be the points in which I have samples. So I need to compute this, and well, let us first do it in matrix form, let's say. This is the basic idea. The covariance of vector u with dimension 3 and vector y with dimension 2 is the expectation of u y transposed. Sorry, this is expectation. And that expectation, if y is cu, y transposed is u transposed c transposed. So taking this c transpose out of the expectation, because it's a constant matrix, I get the expectation of u transposed times c transposed, and this expectation of u transposed is the big K matrix with the covariance kernel of each of the components in the diagonal. So this is it. I just need to obtain big K c transposed, or depending on the component I wish to estimate and the function, either 1 or 2, that I have a sample at x2, maybe one element of this matrix. So if we go back to MATLAB, I have written these expressions again in here. If f or y, is cu, then this covariance is big K c transposed, as I just wrote with handwriting, let's say. And if I now carry out that matrix product, big K c transposed is this thing. So if I now wish to compute a particular element of this matrix, for instance, the one associated to component I and output j, I1, 2, 3, j1, 2, then, well, will be the ij element of this matrix here, and that ij element is this one. For instance, the one that refers to component 2 with output 1, I2, J1 is the 2, 1 element, K2, C1, 2, well, okay, it conforms to this thing. You can pause and think on it, but okay, it's just obtaining the element of a matrix, and then it will be this thing, the one we are going to program in the code, because we need to predict a given component from a given set of samples which have different labels. So for convenience, instead of implementing the big matrix like here, we will just obtain the matrix element we wish as needed. So instead of using a big matrix representation, which could be this one, we will actually use in our code this function as the covariance between a given component at abscissa x1 and a given output label 1 or 2 at abscissa x2, and that function is just implementing the expression we discussed a minute ago. Okay, so with this covariance between test points and test component and samples with a given label, then this KUF is just repeating this kernel for all possible pairs of points. Then this is the basic prediction code. In this line, I compute the covariance of component 1 at a given test points for plotting, just a linear spaced grid, with the samples in which data xi is a matrix whose first column contains the abscissa points and whose second column contains the label, whether sample is from function 1 or 2. Here you have it in the floating window for this example. This second line does the same for component 2, does the same for component 3, and then the mean prediction is, well, covariance between what I wish to predict, U1 at test points, and the information, times the inverse of the information covariance. This information covariance is a matrix. If I have 17 samples, it's a 17 times 17 matrix that, okay, we discussed its computation in the previous video in which we did output prediction. You can just pause and download the code if you wish to inspect or modify it from the link in the description. Well, then these 3 lines here carry out the prediction in mean, and this highlighted line carries out the prediction in variance. The posterior variance is the prior variance minus covariance times inverse of information times covariance transposed. So this is the standard way of computing the posterior variance, and of course the square root of the diagonal is the standard deviation that I can use to plot confidence intervals, and well, I do it 3 times to estimate the confidence interval for each of the 3 components. So this is the main code, and well, you know, the rest is just plotting. Just download and inspect the codes. Let's see the results. In here I have the estimation of component U1 in mean, dark blue, and in confidence interval, cyan dashed lines. Vertical lines indicate the points in which samples of function 1 in blue and function 2 in red, respectively, are available. The common component, it's, let's say, the yellow line in this sample realization. But okay, the sample realization is not the one I took the samples for prediction, so it's just for information that we are trying to estimate the yellow line, but it is not this yellow line, the one we are estimating, it is another one. But okay, in my particular sample set, the estimate of the common component is this one, and well, if we inspect only the standard deviation, we see that our prior standard deviation was 3, but in the region in which we have information, we have a much more precise posterior estimation of my component. And of course, if we get far away from the point in which we have samples, then once we get away from those points, you know, by the amount given by a correlation distance, the distance in which correlation gets negligible, then we would ultimately end up with a posterior variance equal to the prior one. No information. Okay, this is the estimation of the common component. This is the estimation of the component that affects the first output in mean and 95% confidence interval. And if we inspect again only the standard deviation estimation, then this component had a higher bandwidth, lower correlation distance, and so the confidence interval drifts away to the prior in a quicker way. And well, when we have information, we have reduced confidence interval. And well, last, if we estimate component U3, the one that only affects the second output, well, we get this mean and confidence interval estimation that, looking at the standard deviation plot, seems that we do not really have a lot of information on it because the samples do not contribute to reducing its uncertainty with respect to the prior. These samples of F2 reduce a little bit. In this, which I have a lot of samples of 2 and whatever, help reducing a little bit extra. Samples of function 1 doesn't seem to help me anything in estimating the component associated to function 2, which is somehow intuitively expected maybe. And then, well, this is my estimation, and I cannot estimate this thing so well because somehow the third component was the one with lower standard deviation, with lower variance. So somehow its effect is very small compared to the effect of the other components. So we have a very low signal to noise ratio, let's say, in order to precisely estimate this low variance component. So first component, we had a large contribution to the total variability, and we had a large correlation distance. So information from samples at other abscissa locations is useful for prediction over a wide interval. Then, okay, the first component was the easiest to be estimated, and everything helped to narrow the uncertainty band. And on the other side, the third component, we had a smaller correlation distance, so nearby samples provide less information, and it was also a much lower contribution to the overall variance. Then, this was much harder to estimate with precision. So the information we had didn't significantly reduce our uncertainty from the prior, except at this bunch of points here. Okay, we finish here. Let us summarize what we have estimated. In this video, we have estimated hidden components of a statistical model in which we could only observe a linear combination of them as outputs. This is, of course, strongly related to Kalman filtering and smoothing. But okay, in here we just used the time domain correlation, time domain covariance to carry out our estimates, but it's equivalent to Rautenschriebel smoothing. So with the suitable covariance matrices, we were able to estimate this latent factor, these hidden variables, these hidden components from data samples. So this may be used if the components in my statistical model have a meaning which is of interest in my particular application. So we finish here. Thanks for watching.